In our previous lesson, we talked about defining continuity at a point and using that definition to confirm that a function was continuous at a particular point x equals c. Well, what we really want to transition into now is looking at some of our well-behaved functions from earlier and saying not just that it's continuous at a particular point, but we really want to be able to say that a function is continuous over a given interval. And so let's take a look at the function f of x equals the square root of x, just our regular parent square root function here. We know already that the domain of f of x, it's not all real numbers, because remember, I can't take the square root of a negative number and get a real answer. And so the domain is everything from 0 to infinity. Remember that I can take the square root of 0, so 0 is included in that domain, and then it heads towards infinity. And if I look at a graph of this, again, I know that 0 is part of my domain, so the square root of 0 is 0, and then the function has this kind of behavior right there when we look at the square root function. And so what we really want to do is we want to look at this graph and just kind of intuitively, not even thinking about our calculus definition of continuity, we want to be able to say, that f of x is continuous on its domain. Because it absolutely looks like it is. And I will tell you, in fact, it is continuous on its domain. But if you blindly apply the continuity at a point definition, you might run into a little bit of a trouble here, because if you just applied the blind definition of continuity at a point, you would ask yourself, is f of x continuous at x equals 0? And if you just take that definition of continuity at a point from the previous topic, you would say, okay, well, I know f of 0 is the square root of 0, which is 0. So f of 0 exists, and we hit that first bullet point for continuity. But where you might run into kind of a head scratcher is when you address the limit as x approaches 0 of this particular function f of x. And where you might say, hey, wait a minute, what's going on here? Is there is no approaching this function from the left of 0. Everything to the left of 0 is undefined in this function. So if you apply that definition of continuity at a point, you really run into kind of this weird situation where you're not really sure what to say about this. Fortunately, when we talk about continuity over an interval, we're not going to have to apply this strict definition to every single point. So what this lesson accomplishes is it addresses how we speak about continuity over an interval. And we will also consider the endpoints of the domain. And we'll put some formal logic to this here in the next video, but if I want to say that the function is continuous on the intervals from 0 to infinity, that closed off end at 0, I'm not going to look at this idea of the limit as x approaches 0. Instead, if this is the left endpoint, I'm going to look at the limit as I approach it just simply from the right, understanding that that's the endpoint of my domain. And so we'll kind of build the mechanism for that to happen in the next video, but we will in fact be able to say that this function is continuous across its entire domain, including at 0.